Okay, we're going to take a look at these relationships as it relates to their proportionality. And what that means is really how do these shapes tell us this proportion? And we're going to use data tables or numbers to see that. Hopefully this gives us a little bit more of a number sense when looking at these relationships. So the first one, we usually call it a linear graph, but we are also talking, and sometimes it's talked about as a direct relationship. So that is seen by y is proportional to x. That is also our y equals mx plus b, but for now we're going to ignore the plus b part. To give us a little bit better of a number sense, we would want to take a second and make up an equation that we could find some numbers for. So I'm just going to make one up, and instead of m as our slope, it's going to be y equals 3x. So we'll replace the things like the slope, but not our x and y variables. Then you come down and you have this data table. This is just like in math class where they give you a formula or a function and they ask you to solve for y at each of these points where x has a value. So for example, if we plug 1 into x, 3 times x is equal to 3, so y is equal to 3. If you want to try solving those on your own, just to make sure you can do that, feel free to pause now and then play when you want to check your answers. To check your answers, we should have 3, 6, 9, 12, and 15. Now comes the idea that we have to look at how are these numbers, x's and y's, how are they changing as this function continues on. So I like to do this by looking at how what the factor they change by. And what that means is if I'm looking at from 1 to 2, my x value changed by a factor of 2. Now it's a reminder, factor means multiplication, so changing by a factor of 2 means it was multiplied by 2. I then look at how my y value changed. So my x value changed by a factor of 2. Now my y value went from 3 to 6. So from 3 to 6, how did I get there? I had to also change by a factor of 2. The next one, we can look at more than one, but the next one for that would be perhaps going from 1 to 3. I change by a factor of 3. Then from 3 to 9, I also change by a factor of 3. We could continue on and take a look at 1 to 4 or even 2 to 4. From 2 to 4, I change by a factor of 2. And from 6 to 12, 12 divided by 6, how did I get there? You also changed by a factor of 2. It looks as if we have the same change by, the same factor for both x and y. So we're going to scoot this up and take a look. So it says when x increases by a factor of, y increases by a factor of. I'm just going to pick 2 and 2. We could have easily put 3 and 3, but the key point here is that x and y always change by the same factor. So therefore this x and y are always changing by the same factor. We could apply that and add in one extra row to our data table. And if I were to just make up a number, perhaps say that I'm going to go from, or just 20 is my number, that would mean I went from 2 to 20, and I just picked 2 to 20 because that's an easy one to look at. By what factor did I change to go from 2 to 20? I changed by a factor of 10. Now here's what we would want to do. We can cover up our equation so we could try to figure this out using proportions as opposed to plugging it into the equation. So if I changed by a factor of 10 from 2 to 20, that means from 6 to this number, it also should change by a factor of 10. So 6 times 10 is equal to 60. We can double check with our equation. If I plugged 20 in for x, 3 times 20 is equal to 60, so y should be 60. And it worked out. Again, those ideas that this factor, each x and y, is changing by the same factor as seen below. Okay, let's look at one that's not so straightforward. Now on to this inverse relationship, or the inversely proportional one. Let's make up an equation. How about y equals 4 times 1 over x? Go ahead and pause again if you'd like to try to fill out the data table on your own, and then play when you want to see what the values should be. Okay, we should have 4, 2, 1, 0.8, and 0.4. We'll start off like we did last time, and going from 1 to 2, you change by a factor of 2. But now, it's not like before. It's not like going from 3 to 6 that changed by a factor of 2. We're now going from 4 to 2. Our number actually decreased, So instead of increasing, we now have a decreasing value. And by what factor did that change by? It was pretty easy over here because we're used to our multiples, but for a decreasing number, we're not as used to that. So we can take 2 divided by 4, just like you really did over here, 6 divided by 3 to get 2, but 2 divided by 4 actually tells us that it changes by a factor of 0.5. Meaning 4 times 0.5 gets you a value of 2. We can take a look at multiple ones, and let's go to the next one. Maybe we should go to 1 to 4. From 1 to 4, you change by a factor of 4. From 4 to 1, you're changing by a factor of 0.25. This is interesting. We're kind of getting this value that is not the same as before, but now we have something else to look at. If you're looking at how these two numbers relate, meaning my two green ones, my two blue ones, notice that 0.25 is the inverse of 4, and 0.5 is the inverse of 2. As if we would have taken the inverse of 2, that would be 1/2, which in a decimal form is 0.5. Or if we would have taken the inverse of 4, which would be 1 over 4, the inverse of 4, or 1 over 4, is equal to 0.25. So it seems like we have down here that when x increases by a factor of 2, then we're going to state this one a little bit different. Y will decrease, and y changes by a factor of 0.5. So this one is not like our direct relationship. They are not the same number, but this number is always the inverse of this number. So y will always change by the inverse of whatever x changed by. So let's do that in a little bit of an application. And again, add in an extra row to our data table. 20 seems to be my favorite number today. So 20 is going to be my extra number. And then let's take a look at how we change from 2 to 20 again. From 2 to 20, I increase by a factor of 10. Let's cover up that equation so we can solve this using proportions. If I should follow my trend from here, 2 to something should change by a factor of, and it should be the inverse of 10. So 1 over 10 would be simplified into a decimal as 0.1. 0.1 times 2 is equal to 0.2. And we could solve that and look back at that and say, well, does this fit our equation? So if we were to take 20 and plug it into our equation up above, 1 over 20 is equal to 0.01. 0.05. Then if we were to multiply that by 4, 0.05 times 4, y equals 0.2. So that does work out for our column or our row back on the bottom here for our y value. Okay, let's move on to our next relationship, what we call the top opening parabola, or that y is proportional to x squared. So let's write an equation for this one. Y equals 3x squared. Again, go ahead and pause right now if you'd like to try this one on your own, or let it play if you'd like to see the answers. So if we plug in these numerical values for x, 1 squared is 1 times 3, that's 3. 2 squared is 4 times 3, that's 12. 3 squared is 9 times 3, that's 27. Our next ones are 48 and 75. Let's look at our differences again. How does y change when x changes a certain way? So let's look at our x changes by a factor of 2. 1 to 2 is changing by a factor of 2. Y is going from 3 to 12, so by what factor does that change? We would take 12, divide by 3, and you get a value of 4. So it's changing by a factor of 4 to get to 12. We can look at another one and go from 1 to 4. From 1 to 4, we're changing by a factor of 4. Then we have to look at 3 to 48. Again, you would take 48, divide by 3, and that changes by a factor of 16. Just like before when we had to take a look, we have to compare how each x and y change, or by what factor each of them change. So if we're looking at 4 and 16, and 2 and 4, we notice that our y changes by the square that our x changes by. So 4 squared is 16, 2 squared is 4. This is following our proportion exactly. So our x value that changed by a factor of 2, square that, and y changed by that factor. For our inverse one, we had the same thing. If x changes by a factor of 2, our y, take the inverse of that, our y changed by the inverse of that factor, the factor of 2. So down on the bottom when it says, when x increases by a factor of 2, y increases by a factor of 4. So looking at these, y will always change by the square of x's change. So I know I'm kind of saying some of those words and not writing them, but y is always going to change by the numerical value that is the square that x changed by. Let's put that into practice again and go ahead and say, well, if I add another row down here, and let's pick 20, let's go from 2 to 20. So from 2 to 20, I changed my x value by a factor of 10. And covering up that equation again, I'm trying to predict from 12 to what? So if 10 is how my x changed, I need to square that by how much my x changed, and my y should change by the square. So times 100. 10 squared is 100. So 12 times 100 is equal to 1,200. We could, of course, plug that back in to our equation above just to confirm that. So if we were to take 20 squared, that is equal to 400 times 3 is equal to 1,200. So that works again. All right, for the next one, y squared is proportional to x. Now I'm going to rewrite that. I know we talked about in class that there's another way to say that one. And because we tend to manipulate x, or x is our independent variable, we usually like to have y be by itself or have no mathematical functions applied to it. So let's also look at that as y is proportional to the square root of x. And just to make it a little easier, since I have some nice numbers here, our sample equation will be just simply y is equal to the square root of x. Go ahead and pause if you want to try it on your own, or we can take a look at our numbers. Square root of 4 is 2. Square root of 8 is 2.82. Square root of 9 is 3. Square root of 16 is 4. And square root of 25 is 5. Taking a look at how these variables change. So as I go from 4 to 8, 4 to 8 increases by a factor of 2. 2 to 2.82, that's a tough one. We can take in our calculator 2.82, divide by 2, and you get that it changes by a factor of 1.41. Let's try another one. From 4 to 16, we increase by a factor of 4. So from 2 to 4, we increase only by a factor of 2. Just like before, let's take a look and see if we can find any relationship to how each of our variables change, or by what factor. So 4 and 2 and 2 and 1.4. If you recognize that 1.4, it actually happens to be the square root of 2, and 2 is the square root of 4. This is following that same trend that our x changes by some factor and y changes by the square root of that factor as seen in our proportion. So we'll come down to the bottom and we'll change it. When x increases by a factor of 4, y increases by a factor of 2. And again, a point, these numbers could really be anything. I'm just trying to show an example of what they would be. We could have written 2 and 1.41 here, or 9 and 3. It's just trying to show that relationship that we'll write out. So y will always change by the square root of how x changes. So again, this one is always the square root of that. This one was always the square of that, and this one was always the inverse of that. This one was always the same. Let's test our predictions. Add in an extra row. And in this time, I don't think we can use 20. I'm going to pick a number that seems a little bit easier. So I'm going to pick 100. Additionally, let's go from 4 to 100. 4 to 100 increases by a factor of 25. So if we were to cover that up instead of just kind of knowing which one we should do based on the equation, if x changes by a factor of 25, from 2 to this number should change by the square root of 25, which is 5. So from 2 to this value would increase by a factor of 5. 2 times 5 is equal to 10. Then we can double check. If I have 100 as my x, the square root of 100 is equal to 10. Works out again. All right, and our last one, arguably, I think the easiest. This was our relationship that we said no relationship, or more concisely put, y is independent of x. We have y is equal to some number, and that number is always the y-intercept if we had a perfectly horizontal line. So the y-intercept is there. I'm just going to pick a number, and let's just say that that's 3.58. We'll make it as confusing sounding as possible. Y equals 3.58. So if I plug in a value of x, which there's no x up here, y is going to equal 3.58 still. If I plug in 2, there's nowhere to plug it in, so 3.58. 3.58, 3.58, 3.58. Again, y is independent of x. So no matter what the x value, you will always get 3.58 for your y. Down on the bottom, when x increases by a factor of any number, really, y will not change. That's pretty much the sum of independent. Y is independent of x. So we could do our last row in prediction just for fun and say, what if we had 20? This changes by a factor of 20. There should be no change. So 3.58. That's it for the instructions on kind of how these proportions happen with looking through numbers. But if you want to see how some of these can be worked out in story problems or word problems on the back side, we'll flip there and practice a couple now. Okay, let's look at a few of these. I think we'll look at 3 of them. So some samples are given. I think the easiest way to look at these is to write the proportion as you see them. So we'll start, let's try number 2, number 5, and number 7. So number 2, the time cookies spent in the oven is proportional to the square root of the amount of flour used. I'm just going to pick T for time and F for flour, and then I'm going to write it as a proportion. So T is proportional to the square root of F. If you increase the amount of flour used by 4, by what factor will your original oven time change? So this is coming back to that idea that if we increase our X by any factor, the Y will increase by the square root of that. So if F changes by 4, T will change by the square root of 4, which happens to be 2. So the answer is, let's see, oven time will increase by a factor of 2. Not too bad. Number 5 is another type of problem. It's still getting at the same idea. In this one, we have to take a different approach to it. This one doesn't tell us the proportion, but it does give us a graph shape. Notice that this shape looks like a top opening parabola. So that proportion is y is proportional to x squared. So just like on the front, if we change by x by any factor, y will change by the square of that factor. So let's take a look here. I'm given information on the graph. You have x always comes first, right? This is x and y and x and y. X changes from 4 to 8. It's asking what the second y would be. So from 4 to 8, I change by a factor of 2. If I'm changing by a factor of 2, so if x changes by a factor of 2, y will change by 2 squared, or simply known as 4. So by a factor of 4. So then we can take from our y value, 64 times a factor of 4 will get us a value of 256. I simply did that by taking 64 times 4, the factor that y changes, and that was equal to 256. And the last one that I'll show you how to do, number 7. This one kind of gives you a start time, or a start number. The time it takes you to get to school is proportional to the square of the distance you live from school. So again, it tells us this proportion. I'm going to use t and d as my variables, and I'll write that out that t is proportional to d squared. Your commute to school takes 5 minutes. So that's assuming whatever distance you have, your commute takes 5 minutes. If your family moves and increases the distance you live from school by a factor of 4, by what factor will your commute increase? And also, what will your new commute time be? So if we look at this, this would be D. D changes by a factor of 4. D squared is our proportion to time, so time should change by a factor of 16. So that is the answer to the first part. You'll change your time by a factor of 16. And then the second part is asking what your new commute time will be. So if my original commute time was 5 minutes, that's my time was 5 minutes. My distance was something we don't know. But if I increase my distance by 4, my time, or my original time, has to increase by 16. So 5 minutes times 16 gets you a value of 80 minutes. Wow. It sounds like if your parents moved that far, perhaps you should be going to another school. All right. Hopefully that helped out with figuring out these proportions and giving you a little bit better of number sense to look at them with. Enjoy!